Welcome back to the Deep Dive. Today, we are looking at a piece of technology that is, well, it's sort of the cockroach of the electronics world.
The cockroach. I like that.
And I mean that in the most admiring way possible.
Right.
It's survived since 1982. It is in everything from your coffee maker to, the Mars rover, and it just refuses to die. We are talking about I2c.
The integrated circuit protocol. Yeah, it really is the workhorse of embedded systems.
Exactly. And I know what you're thinking. I know I2c. It's two wires, SDA and SCL. You send an address, get a byte. Done. But today we're on a bit of a specific mission. We've pulled the heavy-duty documentation from NXP, who invented it back when they were Philips Plus, app notes from TI, and reference manuals from Microchip. We aren't just talking about how to send a byte. We're going under the hood.
And that is a crucial distinction because, most engineers, they treat I2C as a black box. You hook it up, maybe you throw some random resistors on the line you found on your desk, and you just pray it works. But the reason we're doing this is that I2C doesn't work like modern protocols. It relies on a completely different set of physical rules.
That's the agenda. We're going to unpack the open drain physical layer, why it prevents the magic smoke from escaping when devices fight over the bus.
Right.
We're going to dissect the wired AND logic, we'll compare it to stricter cousins like SM boost, and finally we'll get into the dark art of sizing those pull-up resistors.
Which is where I'd say 90% of I2C problems actually come from.
So let's jump right in. The physics. Basics are simple enough. 2 lines, SDA for serial data, SCL for serial clock, both bidirectional. But you said something earlier that really sets the stage. You said, unlike SPI, I2C doesn't drive the bus high.
Correct. This is the fundamental concept you have to grasp. Most digital logic we use today, like SPI, uses what we call push-pull drivers.
Push-pull. Okay, break that down for us.
Well, it's active in both directions. If a chip wants to send a logic 1, it connects an internal transistor to the positive voltage rail. It actively pushes the voltage up. If it wants a 0, it connects a different transistor to ground. It pulls the voltage down. The chip is always bullying the wire one way or the other.
Asserting dominance constantly.
Exactly. But I2C is open drain. In this configuration, the device can only do one thing: pull the line to ground. That's it.
Just to ground.
Right. Inside the chip, there's a single NMOS transistor. When that transistor is on, it connects the wire to ground. Logic 0.
And when it wants to send a logic 1?
It does nothing.
Nothing.
It turns the transistor off. It just lets go of the wire. The pin becomes essentially disconnected, or what we call floating.
Which is why we need those external pull-up resistors we always see on the schematics.
Right. The pull-up resistor connects the line to the voltage supply, say VDD.
Oh.
So when everyone on the bus lets go, the resistor gently pulls the line up. That's your logic 1.
Okay, so let's unpack why this even matters. Because to me, this sounds like we just made the circuit slower and more complicated. Why not just use push-pull?
It's all about safety during bus contention.
When 2 devices try to talk at once?
Exactly. So in a push-pull system, imagine device A tries to drive the line high, connecting it to power. And at the same time, device B tries to drive the line low,
connecting it directly to ground.
Yes.
You've just created a direct path from power to ground, a short circuit.
Exactly. You get a massive spike in current, things get hot, silicon melts. We call that bus contention smoke.
Not ideal.
But with open drain, think about what happens. Device A wants a 1, so it lets go. Device B wants a 0, so it pulls to ground. What's the result?
The line just goes to ground.
Right, the line goes low. The only current that flows is coming through that pull-up resistor, which limits it to a safe level. So open drain allows multiple devices to drive the bus at the same time without destroying each other.
It's inherently non-destructive. That is actually brilliant for 1982.
It is. And this physical property creates a specific logic function that we call wired ND.
Wired AND. I saw that in the NXP manual. It sounds like we're building logic gates out of copper traces.
We effectively are. The rule is simple. The bus line is high if, and only if, all devices release it.
Okay.
If even one device pulls the line low, the whole bus goes low.
So a 0 is the dominant state. It overrides a 1.
Precisely. Logic 0 dominates. And this isn't just a safety feature, it's the foundation for the protocol's intelligence, specifically clock synchronization and arbitration.
All right, let's see this in action. The multi-master scenario. Because one of the selling points of I2C is you can have multiple controllers, right?
Yes. In practice, it's tricky to code, but the hardware handles the collision negotiation natively.
So let's say we have controller A and controller B. They both see the bus is quiet and decide to start a transaction. They both pull SDA low at the exact same nanosecond.
Right. Now, remember, these chips have their own internal oscillators. They aren't perfectly synchronized. Controller A might want to run at exactly 100 kilohertz, but B might be a little sluggish running at 95.
How do they agree on a speed? Does the faster one win?
It's actually the opposite. This is where wired A&D on the clock line comes in. Remember, if anyone pulls low, the line is low.
Ah.
So let's say controller A pulls the clock low for 5 microseconds, then releases it. It wants the clock to go high.
But controller B is slower. It's still holding the line low for another microsecond.
Exactly. So controller A lets go, but it monitors the pin, and it sees the line is still low.
So it knows someone else is holding it down.
Well, it just knows the line hasn't risen yet. The standard requires it to wait. It enters a wait state until the line actually goes high.
So the bus automatically synchronizes to the slowest device on the line.
Exactly. The low period is determined by the master with the longest low period. They just stay in lockstep.
That is surprisingly elegant. And does this apply to slaves too? I've heard of clock stretching.
It's the exact same mechanism. Say you're reading from a sensor, but it needs a millisecond to go fetch that reading. It's not ready to send the byte yet.
So the slave can just hold the clock line low.
It grabs the SCL line and holds it down. The master tries to release the clock, sees it stuck low, and just waits.
It's the slave saying, hang on a second, don't rush me.
And the master, because of that wired A&D physics, is forced to pause. No software interrupts, no complex handshaking, just holding a wire down.
Cool. So we've synchronized the clocks, but we still have two masters trying to talk. Eventually, they're going to send different data. Who wins?
This is arbitration, and I like to call it the polite fight.
The polite fight. Walk us through it.
It happens on the data line, SDA, bit by bit. Let's say Master A wants to send the binary number 111. Master B wants to send 110.
Okay. Identical for the first two bits.
Right. They both send the first one. Sending a 1 means letting go, so they both let go. The resistor pulls it high. Both masters check the bus, see a 1, think, great, I'm winning.
Same thing for the second bit.
Correct. Now, the third bit, this is the conflict. Master A sends a 1, it releases the bus. Master B sends a 0.
It pulls the bus low. And because of wired A&D, the whole bus goes low.
And here is the magic. Master A is monitoring the bus. It expects to see a high because it let go. But it sees a low.
It realizes it's been overpowered.
Immediately, it detects that mismatch. Master A knows it has lost arbitration. It stops driving the bus, turns off its output, and switches to slave mode just in case B was trying to talk to it.
And Master B?
Master B has no idea anything even happened. It sent a 0, it saw a 0, it just keeps on going. The transmission continues, no data corrupted.
Yeah, that is incredibly clever. It's not collision detection like Ethernet. It's a seamless handover.
It is. Which brings us to an interesting comparison. We often hear I2C mentioned with SM Boost and PNimbus. Are they just different names for the same thing? They're variants, but the differences are critical. SM Bus is System Management Bus. Intel defined it in '95 for motherboards. It uses the I2C physical layer, but it adds discipline.
Discipline how?
Well, standard I2C is a DC bus. The frequency can drop to 0 if a slave device crashes while holding the clock low.
Like we talked about with clock stretching, but it never lets go.
Exactly. In standard I2C, the bus is dead. Forever. SMBus introduces a mandatory timeout, usually 35 milliseconds.
That's specific.
If a transaction takes longer than that, every device has to reset its interface and release the lines. It stops one buggy sensor from taking down the whole system.
That seems like a safety feature I'd want almost everywhere. What about voltage levels?
That's another big trap. I2C logic levels are usually relative to VDD. A low is 30% of VDD, high is 70%.
So at 5V, your thresholds are different than at 3.3V.
Exactly. But SMBus often uses fixed TTL levels 0.8V for low and 2.1V for high. This can cause issues if you mix a 3.3V I2C chip with a 5V SMBus chip. Your noise margins could vanish.
And PMBus.
PMBus, or Power Management Bus, is a command language built on top of SMBus. It defines specific commands for power supplies.
Like tell me your temperature or set voltage to 1.0V.
Right, and PMBus almost always uses PEC packet error checking.
A CRC check.
Yes, a CRC 8-byte at the end of the message. If the checksum doesn't match, the receiver rejects the data. Standard I2C rarely does this.
Okay, so that brings us to the hardware. Sizing that pull-up resistor.
Yeah.
The TI node called it the Goldilocks problem.
It truly is. You can't just grab a 10K resistor from the bin and assume it'll work.
I feel attacked right now because that is exactly what I do.
And it works for slow speeds, but here's the engineering reality. You have two opposing forces. On one side, the current limit of the transistor. On the other, capacitance.
Okay, let's establish the boundaries. Why can't the resistor be too small, like a 100 ohm resistor? The signal will be strong and fast, right?
Incredibly fast, but remember that tiny transistor inside the chip? When it tries to pull the line to ground, it has to fight that resistor. With a 100 ohm resistor on a 3.3V bus, you're trying to sink 33 milliamps.
Is that a lot?
For an I2c pin, yes. The spec for low-level output current, or IOL, is typically 3 milliamps.
3 milliamps, wow. So 33 mA would fry it.
Or, even if it doesn't burn out, the transistor has internal resistance. If you shove too much current through it, the voltage at the pin might not hit zero. It might float up to 0.6V or 0.8V.
Which might not look like a logic so to the other chips.
You've ruined your noise margin, so that sets your minimum resistance. You take your voltage, 3.3V, divide by 3 mA, and you get about 1.1K ohms. You cannot go lower than that.
Okay, so stay above 1K. What about the other side? Why can't I use a huge resistor like 100K? That would save power.
It would, but now you're fighting capacitance. Every trace on your PCB, every pin on every chip adds stray capacitance to the bus.
And capacitors take time to charge.
Right. Think of the bus capacitance as a bucket. The pull-up resistor is a hose filling it. When the chip lets go for a logic 1, the resistor starts filling the bucket. It's not an instant snap, it's an exponential rise.
An RC time constant.
Exactly. A huge resistor is a very skinny hose. It takes a long time to fill that bucket to the logic 1 threshold. That's your rise time.
And the spec has limits on this.
Strict limits. For standard mode, 1,000 nanoseconds. But for fast mode at 400 kilohertz, it must rise within 300 nanoseconds.
Oof, 300 nanoseconds is fast. So if my resistor is too big, the signal rises so slowly the master tries to read the next nip before the line has even reached high.
Precisely. You look on a scope and see these weird shark fins instead of square waves. Eventually, the device stops seeing ones.
So that's the trade-off.
Yeah.
Small enough to charge the bus fast, but big enough not to blow up the transistor.
And that window gets narrower as you go faster. If you want to run at 1 megahertz fast mode plus, the physics gets really tight.
How do they manage that?
The spec changes. FM plus devices need stronger drivers that can sink 20 milliamps way more than the standard 3. This lets you use much stronger or lower value pull-ups to fight capacitance.
Bigger muscles to pull against stronger springs. Now, what about mixed voltages? Classic maker problem. 5V Arduino, 3.3V sensor. Can I just hook them up?
Please don't. That is the easiest way to kill a sensor.
Because of the pull-up.
Yes. If you pull up to the 5V rail when the bus is high, you are feeding 5V directly into the pin of your 3.3V sensor. Unless that datasheet says 5V tolerant, you will blow the internal protection diodes.
So what's the fix?
The proper engineering solution is a dedicated level shifter, like the PCA 9306. It isolates the voltage domains while passing the signals.
Seems much safer. Okay, before we wrap, one advanced trick from the NXP manual for really heavy buses. Switched pull-ups.
Ah, yes. This is for when you're really pushing the limits of capacitance, like running I2c over a long cable.
And the rise time is just too slow.
Right. So the idea is you have a standard power-saving resistor for the steady state, but specifically during that rising edge, a circuit detects the transition and temporarily switches in a second, much lower value resistor in parallel.
Like a turbo boost for the rising edge.
Exactly. It slams the line high to meet the 300 spec, then switches off to save power. It's complex, but it solves the problem.
That's very cool. It really shows how much depth there is to this simple two-wire protocol. It's analog engineering in disguise.
It really is. It's a delicate balance of physics.
So let's bring it all home. What's the big takeaway for you?
For me, it's the elegance of the open drain design. It turns a potential electrical disaster, a short circuit, into a logic function. The wired ND isn't just the circuit, it's the logic of the protocol itself, happening passively by just obeying physics.
It is clever. And looking forward, is I2C going to be around for another 40 years?
Hard to say, but we are seeing MIPI i3c starting to emerge. It's backward compatible, but it supports in-band interrupts and much higher speeds. It's an evolution.
Evolution, not revolution.
Exactly. But I2C will be on your cheap microcontrollers for a long, long time.
My aha moment today is realizing just how much depends on that passive pull-up resistor. A sophisticated microcontroller running millions of lines of code tries to send a one war, and it does nothing. It just lets go.
It relies entirely on that external resistor to do the work.
If that resistor falls off the board or you sized it wrong, the silence is deafening. The chip can't shout a 1. It can only whisper a 0 and hope the resistor speaks up.
That's a good way to put it. The resistor powers the 1. Without it, the bus is mute.
Thanks for diving deep with us today. Check your rise times, calculate your RC constants, and we will catch you on the next deep dive.
Happy engineering.